Hi everyone, welcome back to my channel. Please do like, share, and subscribe to my channel. This is Varsha from SVC Bangalore 24CS2706 from BE first year CSC department. Now I am going to discuss about mathematics under that Markov analysis. Markov analysis, uncovering patterns in stochastic processes. Welcome to this presentation on Markov analysis, a powerful tool for understanding and predicting the behavior of the system of evolve over time in a probabilistic manner. We will explore the fundamentals of the Markov processes, delve into the application across various fields and discuss the limitations and future direction of this fascinating area of mathematics. Introduction to Markov processing. Defining Markov processes. Markov processes are the powerful mathematical models that describe systems evolving probabilistically over time. They are characterized by a fundamental property known as the memoryless or Markov property. This means that the future state of the system depends solely on its present state, with no influence from the past history to the system. This unique feature of Markov processes sets them apart from other stochastic models as it allows for simplified analysis and prediction of the system's behavior. We can see in the picture. This is an example for Markov processes. Markov's rule in mathematical applications. Markov's rule, also known as the Markov's property, a fundamental concept in probability theory and stochastic process. It states that the future state of a system depends only on the present state, not on the past state. Probability modeling, optimizing problems, time series analysis. Markov's rule allows us to model and analyze stochastic processes such as the random walks, quick queuing systems, and population dynamics, where the future state is determined solely by the current state. Optimizing problems. Markov decision process, which rely on Markov's rule, are used to solve optimizing problems in areas like resource allocation, inventory management, and reinforcement learning. Next is time series analysis. Markov models such as Markov chains are used to analyze and forecast time series data in fields like finance, economics, and engineering, where the future value depends on the current value. By leveraging Markov's rule, mathematicians and researchers can develop powerful models and algorithms to understand, predict, and optimize complex systems in the wide range of applications. Markov's rule in action. Consider a simple random walk on a number line where a particle starts it at a position 0 and moves either one step left or one step right with equal probability at each time. Starting position, the particle begins at position 0. Step 2, a particle next moves depends only its current position, not on the previous steps. This is Markov's rule action. Step 3, step 1, the particle moves either left or right with a 50-degree chance. This is step 1. Markov's rule application is step 2, and this side the particle begins at position 0 is the starting position. This is the better explanation for the Markov's rule in action. Using Markov's rule, we can calculate probability of the particle being at an position after n steps. This allows us to model and predictable and behavior of the random walk over time. Next is fundamentals of Markov chains. First, states. Markov chains are specific types of Markov process with a finite number of states. These states represents the possible conditions of configuration systems can be in. Second number states, that's the Transitions between the states occur based on probabilities, defining the likelihood of moving from one state to the another. These probabilities are represented by the transition matrix. Step 3 says that the time steps. Matrix change progress through discrete time steps where the system's state is evaluated at specific points in time. This allows us to model the system's evaluation over time. Transition matrices and stationary distributions. The first image represents the transition matrix. Next is the stationary distribution. Next, relationship and meaning of the transition matrix as well as the stationary distribution. First, let's look at the transition matrix. This matrix shows the probabilities of moving between states in a Markov's chain. Each cell represents the probability of transitioning from one state to the another. Next, stationary distribution. The above graph illustrates the long-term probabilities of being in each state. It shows how system settles in a steady state over time. Okay. The next is a relationship and meaning between transition matrix as well as stationary matrix. The stationary distribution is derived from the transition matrix. So by this sentence we can understand that the roots of the stationary distribution is the transition matrix. It represents the equilibrium state of the Markov chain where the probabilities of being in each state remains constant. Next is ergodicity and steady state behavior. Ergodicity. Ergodic Markov chains reach a steady state over time, meaning the long-term probability of being in each state stabilizes regardless of their initial state. Now, next step is the steady state. In steady state, the system exhibits a predictable pattern and the stationary distribution accurately, reflecting the long-term probabilities of each state. The third step, applications. Ergodicity is essential for many applications of Markov analysis as it allows us to make long-term predictions and understand study diseases progressions, treatment evaluation, and patient's care. Thus, simulate disease trajectories and predict outcomes. Applications of Markov analysis. First, we studied three. The fourth one is network performance. Fifth, customer behavior modeling. Sixth, nature language processing. First, network performance. Markov chains analysis and optimize network performance. Customer behavior modeling. Markov models predict customer churn and optimize marketing. Natural language processing. In NLP, also the abbreviation for the natural language processing is the NLP. Markov models handle language modeling. Market modeling and forecasting. 20% growth. Markov models help forecast market growth by analyzing historical data and identifying patterns in price movements. Revenue 10M. Predicting $10M revenue. Predicting revenue streams for companies based on customer behavior, market trends, and product demand. 10% risk. Assessing market risk by simulating different scenarios and evaluating potential outcomes using Monte Carlo methods. In physics also we used to study the Monte Carlo methods. Engineering, they introduce Monte Carlo methods. Optimal decision making with Markov processes. Dynamic programming. Markov decision processes MDPs allow for optimal decision making in systems with uncertain outcomes, finding the best policy to optimize reward over time. Reinforcement learning. Markov processes play a key role in reinforcement language learning algorithms where agents learn optimal decision making with Markov processes. Dynamic programming. Markov decision processes MDPs allow for optimal decision making systems with uncertain outcomes, finding the best policy to maximize reward over time. Next one is reinforcement learning. Markov processes play a key role in reinforcement learning algorithms, where agents learn optimal actions through trial and error. Applications. MDPs are used in various fields including robotics, resource allocation, and game theory. Limitations and assumptions of Markov analysis. Memoryless assumption. The memoryless property, while simplifying analysis, may not always reflect reality. The past can sometimes influence the future. Stationarity. The assumptions of stationary transition probabilities might not hold the dynamic environments where the system's behavior changes over time. Data availability. Accurate and sufficient historical data are crucial for building and validating Markov models. Limited data can lead to unreliable results. Conclusion and future directions. Markov analysis provides a powerful framework for understanding and modeling stochastic processes with wide ranging applications across diverse fields. Future directions include developing more sophisticated models, integrating machine learning, and exploring applications in areas like quantum computing and complex networks. Thank you. Thank you for watching my video.